In this lesson, we're going to take a look at energy, power, and intensity as they relate to waves. So first thing we want to do is we want to understand how much energy is transported by a wave. When a wave comes in and hits some matter, what it actually does is it causes the particles that make up that matter to start vibrating, to start undergoing simple harmonic motion. And you can think of these particles as connected to the other particles or to little springs or whatever. So there is a restoring force that's going to put them back where they should go. Well, remember, in simple harmonic motion, the energy of a particle is given by 1/2 Ka squared, where A is the amplitude of the displacement of the particle and K is the spring constant. So that'll change depending on the elasticity of the material. But remember, K also shows up in the equation for frequency. Frequency is equal to 1/2 pi times the square root of K over M. If we solve this equation for K, then we can substitute K for frequency and mass, so we're looking at the more readily measurable quantities of the wave. So then we get 2 pi times F equals the square root of K over M. We're going to square both sides, square, square. So we get 4 pi squared F squared equals K over M, and then multiply by M, and we get K equals 4 pi squared F squared M. We're going to go ahead and substitute that back into this equation. So half of 4 is 2, so this equals 2 pi squared F squared M times A squared. And so this tells us right away that the energy carried by a wave is directly proportional to both the amplitude squared and the frequency squared of the wave. So increasing the amplitude increases the energy, and increasing the frequency increases the energy of a wave. Now, waves transport energy, so it's not just enough to talk about how much energy that a wave transports, but also we should talk about how quickly a wave transports energy. And so when we talk about that, we're taking energy divided by time. Now remember, energy is measured in joules. Energy divided by time describes power. So power is energy divided by time. It's measured in watts, a joule per second. And so, I mean, this is just 2 pi squared F squared M A squared over T. Now, we can make some substitutions with M in terms of density and volume if we want to, so that we can deal with this on another level. But for now, I'm just going to leave it like this. The last thing I want to look at is intensity. Okay? Intensity is a little bit different than power or energy. Energy is telling me how much energy is being transported. Power tells me how quickly that energy is being transported. Intensity actually has to do with how that energy is distributed. So if you think about a speaker sitting in the middle of a room, it sends out waves, but not just in a circular pattern, actually in a spherical pattern. They move out in all directions. Well, if the power output is constant, that means it's always producing the same energy per second. By the time the wave gets to here, that energy is spread out over a much greater surface than it was when it was in here. And so the actual amount of energy moving through this area compared to the amount of energy moving through that area is much less as we get further from that. So intensity is actually power divided by area. And I'm going to use S for area because I'm already using A for amplitude. Now, as this gets further out, what happens to the area? Well, it depends on the shape, right? For this thing, for this 3D wave, the surface area of that wave is given by 4 pi r squared. So in 3 dimensions, intensity is power divided by area, so we have intensity is equal to power over 4 pi r squared, which tells me right here intensity is inversely proportional to the radius squared, or the distance from the source squared. But the other thing that's cool is energy is directly proportional to power, and energy is directly proportional to amplitude squared, and power is directly proportional to intensity, which basically tells me that amplitude squared is inversely proportional to r squared, right? All I'm doing is making substitutions. Well, this, I can say, well, what if we compared a wave A1 at a distance, or the amplitude of the wave at a position 1 to the amplitude of a wave at position 2? And I'm just going to go ahead and divide these. Since they have a proportionality, I can rewrite this as an equals, so a1 squared over a2 squared is equal to 1 over r1 squared divided by 1 over r2 squared. Now, if I just invert and multiply that fraction, it tells me a1 squared over a2 squared is equal to r2 squared over r1 squared, square root both sides, and I can see that a1 over a2 is equal to r2 over r1, which means if I get twice as far from the source, my amplitude will be cut in half. These are inversely related to each other without the square factor. Now, this was true because the area of the wave increased directly proportional to the distance squared. What about a wave moving along a string? How does its area change? Well, it doesn't. That's a one-dimensional wave. Its area is fixed. It's always moving through that string, which means its amplitude doesn't decrease because its power doesn't change and its intensity doesn't change, right? All of the energy is contained to this string, so assuming there's no damping going on, then the amplitude here and the amplitude here is going to be the same. Because right here, I have intensity equals power over area. So if I have the area S1, so I have the intensity at point 1 over the area S1, this should be equal to the intensity I2 over the area S2. But if S1 equals S2, that means intensity at 1 is equal to intensity at 2. And if the intensity at 1 and 2 are the same, that means the power is the same. And if the power is the same, the energy is the same. And if the energy is the same, the amplitude is the same. Okay? So for a one-dimensional wave trapped on a string, we don't actually see this decrease in amplitude like we do for a three-dimensional wave, right? Now, on this three-dimensional wave, you hear that. The further you are from a speaker, the softer the sound hears, the softer the sound is because the energy is spread out over a large area. But as we move that wave along a string, the wave doesn't decrease because all the energy is trapped on the string. Now, there's one more case to consider. We've looked at a three-dimensional wave and a one-dimensional wave. What about water ripples moving out from a splash? That's not one-dimensional or two-dimensional, or three-dimensional. That's a two-dimensional wave if you think about it, because it's not increasing to fill the space, rather it is just making its circles bigger and bigger and bigger. So I'm going to leave that as an exercise for you to figure out how is the amplitude related to the distance from the source on a circular water wave.